Hi class, welcome back to Electromagnetics. So we've gone through all of Maxwell's equations in the integral form. Now we want to circle back through and look at each of them again, but this time in differential form. Quick thought for the day. This comes from Proverbs 30:24 through 28. It says, "Four things on the earth are small, but they are exceedingly wise. The ants are a people not strong, yet they provide their food in the summer. The rock badgers are a people not mighty, yet they make their homes in the cliffs. The locusts have no king, yet all of them march in rank. The lizard you can take in your hands, yet it is found in the king's palaces." So I thought this was a pretty fitting verse because as we start to look at these fields in differential form, we're going to shrink them down to, infinitesimally small points and see what's happening there. But just because this is at a small point doesn't mean it doesn't have some effect on the bigger picture of what's going on. But just sometimes we need to look at in a localized, very localized spot what's going on. So I thought it was fitting from this verse that just because things are small doesn't mean they don't have a great impact. Everything has its place and effect in the world that we see. So this will officially kick off part 3 of the course. So again, we'll have 6 little mini lectures. The first 2 we're going to take Faraday's Law and Ampere's Law, take them down to differential form. I'm going to take a little break then, and we're going to introduce a theorem that maybe you've seen before, probably not though, on curl and what that means, and Stokes' theorem. Then from there we'll look at Gauss's law for electric and magnetic fields, again down to the differential form, and finally introduce one more theorem, which is the divergence theorem, which is pretty handy when dealing with fields. So like I said, we've explored Maxwell's equations in integral forms, and again, these give us representations of the electrical and magnetic fields and their interactions at a system level, such as with the line integrals, which we've looked at extensively, and surface integrals, again, we've looked at those. But they don't allow us to view the interactions down to individual point levels. So for that, we have to derive or maybe rederive Maxwell's equations in differential form. So to do this, we will take the original equations that we derived in the integral form and we will shrink them down around these closed paths, smaller and smaller. So the first one we're going to look at is Faraday's law. So we recall from the previous lecture where we derived it that this is the form of it. So it basically means that if we take some closed loop and we integrate or sum up the E field along the length, and again this length is a vector length, so it has a direction, so the E field that's in the direction of the path, if we sum that up, it should equal to the time derivative of the magnetic field passing through the surface that's bounded by this curve. So any of the magnetic field that's penetrating this surface going through there should contribute to an electric field along the path of the length. Again, where S is any surface bounded by C. So to do the differential or to demonstrate how this works, we want us to consider an electric field that only has an X component, that is, it only has an EX. EY and EZ, which are in the Y and Z directions, they don't have any component there, so it's zero. There's no change there. So that means that this field only depends on its location on the Z-axis and time. So that means it travels in the Z direction. So the general form of the way this would look then is our E vector would equal to some EX, which is only dependent on its position on the Z-axis and time, and it's only going to vary in the X direction. So to frame this problem, we now want to look at this, examine it over a rectangular path that's parallel to the XY plane, and we're going to take that path and we're going to shrink it down to a single point. So here's a diagram kind of showing that path. So we have our z-axis to the right, our x-axis down, and our y-axis is going into the sheet. Okay, so this plane then is parallel with those planes, and so you can see here then as we move along this path, we'll have delta z. So z is the only thing that's varying. X stays the same, and so it's just from z to delta z. Same thing down here, z to delta z. And it'll still be delta z just going in the other direction. So going up and down, our x are going to change. So we'll go from x to delta x. So that's our delta x total length. And the z doesn't vary on either one of these. We also need to keep in mind that we only have an ex component. So our e value only is going to show up on these two parts of the circle. There shouldn't be any E field contributing here because there's no Z component. There's only an X component like we said on the previous slide. So the easiest way to do this, since it's a square, is to integrate around this closed loop, and we'll look at each of the four legs, right? So first one is we'll go from the point XZ, which was that top corner, and we'll go across what was the top before, that Z plus delta Z, and so it'll be the E dot dl equal to 0. Remember that one, that loop is going in along the z-axis, and we said there is no z component. So this integral, by definition, is going to equal to 0. So now if we come down the outer part of that square, we're going to go, our x is going to go from x to delta x, and our z plus delta z is going to stay the same. So we're actually coming down that side. So in that case, we do have a non-zero E field because that's moving in the x direction, or that wire is going, or whatever part of the path is going in the x direction. So then that'll just simply be the E field, which is EX at the point Z plus ZX, or along Z plus ZX, and then times our DL, which is just our delta X. That's the distance we travel down, is delta X, if you look back at that previous graph. So again, if we come across the bottom, it's the same thing. Our x stays constant, and then our z is moving, so it's that part of the path is moving along in the z direction, but remember we said there is no z component, so again this one's equal to 0 by definition. And finally, if we come up on the left side, we'll have the same thing as we did before, our ex evaluated at z, because z is constant, and again it's going a length of delta x. So conveniently, in this case, the first and third terms go out to 0 by definition because they're in the z, moving in the z direction, so we're only left with the x components. So now if we sum up everything around this path, we only have those two components left, so it'll be the exz plus delta z times delta x minus ex evaluated at z times delta x. So that's the left side of our equation. So we can pull the delta x out, that's a constant, and rewrite it in this form, so that'll be handy for us here in just a second. So now we want to think about the right side of that. So the right side of that equation, remember, is just the time derivative of the magnetic field that's going through that surface area, which in this case is just the box, how much is going through the box. And so that means we need to only consider a b vector with a y component, because that y component is what's going to be perpendicular to that box that's in the xz plane. And so that means we'll simply have a by component evaluated at x and z, and it's going to be times the surface area, which is, remember, just the delta x was the x length, and the delta z was the horizontal length. And so this gives us what we can see on the right side of that equation, just when you take the differential with respect to time, the derivative with respect to time. So again, these two are 0 because we only have an ex component, so it's only moving in this direction, so these are 0. And remember, our whole area is this box, and so this length is delta x and this length is delta z, so that's why that's that surface area. So hopefully that makes sense to you. So if we take these expressions and we substitute them back in to our original equation, we have this. So remember, we had our difference in the e's times this delta x on the left, and then we've had this for our magnetic field that's traveling through that surface, and we have to take the time derivative of that. So let's look at this a little bit and let's rearrange things just a bit. First thing we see is there's a delta x on both sides. You can pull the delta x and the delta z actually both outside of this because they don't vary with time. And so the delta x's will cancel, right? And so then we can divide both sides by delta z. So that brings this delta z over here. So now if we take a look at this, it may dawn on you that this looks hopefully pretty familiar to you, at least if you look at the left side for sure, that should look familiar to you. Hopefully you'll be able to recall from your calculus days that this is the basic definition for a derivative. You know, the change in two values divided by the distance between those two points of evaluation. But the way we turn that into a full derivative is we need to take the limit, right? So that's what we're going to do. We're going to come over to this side, and we're going to take the limit as x, delta x and delta z go to 0. So what that's basically doing is taking our original box, that's going to shrink it down, shrink it down, shrink it down until you get to a point, theoretically. And so now this for sure is the definition of a derivative of e with respect to z. Nothing over here is really going to be affected much by the delta x and delta z going to 0, except that your by evaluated at that point. But we are doing that. So if we do that, then we can rewrite this in a much cleaner form than this. So this is the partial derivative of the EX component of the E field, which is all we have in this case, times the partial Z, and that's going to be equal to our B field, which only has a Y component with respect to T. So this is Faraday's law in differential form, at least for this incredibly specific case. So this is a very special case. Remember, we said only an EX component, and we only have a magnetic field in the Y component. So using a similar analysis there, just was making everything super general and adding the multiple components for X, Y, and Z, and assuming that they can all be time dependent. And so this is super general. We can now derive the general form of Faraday's law in the differential form. And it comes to this, and so you can see we're just taking the difference in the perpendicular components with respect to the perpendicular directions for the E field, and then over here we're just taking the time derivative for each component in the direction that they're going. Well, this is kind of complicated. We have some shortcuts that we can do to simplify at least the notation for this. So first thing you might have realized already is on that left side, we can write this in the form of a matrix and then do the determinant like we did when we do vectors. And so if we were to do that cross product pattern that we talked about in the review, that would give us what we had on the previous page for the EX for the left side of the equation. So if we were to expand that out, again using that cross product method, this is what that would look like. Well, we need to stop here for a minute and look at this, because then hopefully we see some things here that might pique our attention. So the first thing is this term right here. Do you recognize what this term is? Well, hopefully you see that it's the EX in the X direction, the EY in the Y direction, and the EZ component in the Z direction. So this is basically just the definition of the vector electric field intensity vector, or E. So that's just that vector. So the right-hand side of the cross product then is the definition of the E field vector, so we can rewrite it at least like this. So this looks a lot better, right? So now we have all of this crossed with the E vector, or the electric field vector. Well, we have another thing that can help us out. So the left-hand side of this vector, this is a special known differential operator that's used a lot in mathematics, especially when dealing with fields. and we call this the del operator, and it's signified by the bold-faced upside delta sign symbol. And so this operator then is defined as this. So anytime you see this, you can think to replace it with the right-hand side of that equation. So if we make that substitution, we have now del cross E is equal to, or del cross the electric field is equal to the partial derivative of the magnetic field with respect to time. So this is the general form of Faraday's law in differential form. So let's take a minute and see, work a couple examples here, make sure we see how to apply this and what it does for us. So first example is we're giving a magnetic field defined by some amplitude times cosine omega t in the y direction. So this is a sinusoidal field or component in the y direction only. There's only a y component. And it's told us then, or it's known that the E only has an x component, so therefore we only have an EX. So from what we have learned here, then we know that the partial of EX, or the E field, which only has an x component with respect to z, is got to equal to the negative partial derivative of the magnetic field with respect to time. Well, we were given what that is. That's this side of the equation here. And so we plug that in, and we take the derivative with respect to time, and when we do, it adds this omega term and changes this to the sine omega t. So therefore, if we want to find out what EX is, we have to integrate both sides with respect to z now to get rid of this partial derivative with respect to z. So what it means, we integrate this side with respect to z. So when we do, that now adds the z component to our original equation. Nothing else is dependent on the z location, so this is the final answer then. So our EX is equal to this. So if we add an E in the only in the x direction that look like this, it's going to produce a magnetic field of what we were given to start with. So one thing to note then is a uniform magnetic field will give rise to an electric field varying linearly with z. So you can see it varies with z. One last example I want to look at, just make sure we understand this del operator and how it works. Say we're given this arbitrary field. It could be an electric field, but it doesn't matter. But it's defined as YAX minus XAY. And so they want us to find del cross A. So if we use this determinate expansion for the curl of the vector, so incidentally this is what's called the curl of A. So when we see it in Faraday's law, it's the curl of E. That's what we call that. So the curl of A, or del cross A, would be take this in matrix form and do our little matrix cross product exercise on that. And so what we have then is in the A direction, it's the partial of z minus x. In the y direction, it's the partial of y in respect to y. And then in the z direction, it's the partial of negative x minus the partial of y. And so when we do that, these two cancel out. And what we're left with then is negative 2 in the AZ direction. So that's how you take the curl of a vector, or del cross of a vector.